Okay, hi everyone. As she introduced me, I am Giulia Martino, and the talk we're going to have today will be focusing on two ROP techniques, which are called SROP and ret2dlresolve. We're going to see an overview of them and how they could be useful in some situations while we're struggling, like during a CDF, for example, with some binary exploitation challenge. I will start with a quick introduction about myself. I am 25 years old and I was born and I still live in Genova, in Italy. I currently work at the Cybersecurity National Laboratory, where we do cybersecurity research and education. And I'm also still a student at the University of Genova. In my free time, I really like CDFs and I really love binary exploitation. Okay, what are we seeing today? This is the outline. We will start with a quick introduction about ROP technique in general, just to refresh the concepts. Then we will go directly into the two techniques, and for each of the two techniques, we will see a common scenario, so a situation where the technique can actually be useful for you. And then we will see some background knowledge needed to understand both of the two techniques, and finally see how to apply that knowledge in order to perform the exploitation part. Just a little disclaimer before starting with the talk. I will be referring to x86-64 architecture during the talk. Similar considerations could be made for other architectures. It's just so that you know it, because I will mention some register names and so on. Okay, the introduction. Basically, the whole reason behind the existence of the ROP technique is here in the slide, and it's the fact that the stack contains return addresses. In order to understand it, we can start with a very simple example, and we can imagine that we have a function called foo, and that inside this function, there's a call to another function, which is bar. If we imagine the execution of foo starting, then at some point when the call to bar happens, the execution will have to jump from the code of the foo function to the code of the bar function, and then bar will start executing as well, and as soon as the return statement happens, the code will have to return back to foo. So basically, it will have to go back where it was before, and specifically, the instruction, well, the execution will resume afterwards, will be this one highlighted in the slide. So exactly the instruction after the call to the bar function. So the address of this instruction is what we intend when we say return address. So this is a return address for the function bar. And this is stored inside the stack. So basically, what a return statement does is just simply taking an address from the stack and jumping to that location. And this has a very big implication, which is that if we are somehow able to control the stack, then we could be able to change those return addresses inside the stack and be able to force functions into returning somewhere else, into some arbitrary location that we can control. And this is exactly what the ROP technique does. It's basically an exploitation technique that it's based on overriding return addresses inside the stack in order to obtain the hijack of the control flow of the program. So coming back to the example we've seen before, we imagine that we have this call to foo, and that foo calls bar, and that the return statement happens. We also assume that we can control this return address, so we can basically redirect the return statement to an arbitrary block of code. But what happens if the arbitrary block of code contains another return statement? What will happen is that, since we have seen what return does, it will just go and take another address from the stack and will go and jump to that location. So basically, as long as we hold the control under the stack, we can go on repeating this process, and we can go on repeating the hijack of the control flow. So we can finally get to describing the ROP gadgets. They're basically sequences of relatively small sequences of instructions that always end in a return statement, so that they can be chained together. And what we do when we create a ROP chain is that we basically return from one gadget to another one, And in using those little pieces of code, we basically build a very bigger code which does whatever we want to achieve with our exploit. Okay, so this is all for the introduction. Now we will start talking about the first technique, which is called SROP. We will start with a scenario, as I said before. So we will imagine that we already have what we just talked about. So we have the control flow hijacking, because somehow, for example, using a very big buffer overflow, we managed to override return addresses inside the stack. And our goal is to ROP, so to apply the technique we've just seen in order to spawn a shell. A possible approach for this problem is, okay, if we want to spawn a shell, then we can try to call, to execute a syscall instruction, specifically the execve syscall, which is used for executing programs. And in order to be able to do that, we have to set 4 registers to the values that you can see here in the table. And the first register is the syscall number, which is 0x3b, that represents execve. And then we also have RDI, RSI, and RDX, which are just the parameters for the call to the syscall. So it's the address of binsh, then 0 and 0 again. What could we do? So a possible usable exploitation flow with a ROP chain could be, okay, we can basically decide to split our exploit in 5 blocks, and each of the block will take care of 1 register. So we will start with setting the RDI to the correct value, then we will go on and go on again until we have all the registers perfectly set, and we can finally jump to a syscall gadget. And when we jump to the syscall gadget, then execv will be executed with all the parameters we need, and so we will actually be able to spawn our shell. But the problem here is, what if some gadgets are missing? Here we're assuming that we have all the gadgets needed for building such a long ROP chain. And this is not always possible, and this is one of these situations where you can really, really struggle while doing binary exploitation, because you're here, you have everything, but you're just missing one single gadget, and you say, okay, what can I do now? And this is where SROP comes in to help for us. And in order to understand how it works, we will start with talking about signal handling in general in most POSIX systems, which is some background knowledge just to understand it. Basically, whenever a signal is delivered, the kernel needs to perform a context switch in order to give the execution to the signal handler, which is a function that will handle the signal and do whatever it needs to do. The first thing the kernel will do, it's saving the current execution context inside the stack. So it will basically be doing a sort of snapshot of the entire execution context so that it will be able to restore it afterwards. And it uses a structure which is called sig context. And we don't really need to understand how it's made in all the details. We will see a sketch of it later. Then the context switch happens. So the signal handler starts its execution, do whatever it needs, and as soon as the signal handler is done, what will happen is that the sig return system call is called. So what does this system call do? It basically just tells the kernel to go into the stack and restore the entire execution context from that structure that we had pushed before. So at the end of all these steps, everything goes back as it was before. We had saved the execution context, we had switched it, and then we had restored it back. Why is this interesting for us? Because basically the sig return syscall just takes values from the stack and restores the execution context. But when we say execution context, we also mean the entire set of registers. And the entire set of registers will be taken from the stack and restored. So since we know that we are talking about a scenario where we can control the stack, so what can happen if we can execute that syscall and we can also control the stack? What we do is that we can fake a sig context structure inside the stack and then call the sig return syscall. So here you can find an example of a possible sig context structure. that you can fake inside the stack. And there's a lot of fields that have been dotted out because they're not relevant now. But what we need to focus on is that we have the 4 registers that we have seen before. So we can put this structure here inside the stack, just setting all the registers we have seen to the values we need for executing the execve syscall. And then we also have a 5th register, which is RIP. RIP is the instruction pointer, and it's a register that holds the address of the next instruction. So if we set RIP to the address of a syscall instruction, what will happen is that as soon as the sig return syscall will be done, this will be the values in the registers, so the execution will start back from here because RIP is pointing to instructions of a syscall. And specifically, the syscall that will be executed will be execve because RAX is equal to the syscall number of execve. And it will be executed exactly with the parameters we want because everything will be already perfectly set. So if we go back to the scheme we had before, so when we had the execve syscall here, and we had to build a ROP chain in order to call that syscall, basically we had to control all these 4 registers, but now in order to be able to execute the sig return syscall, we only need to control RAX, so it's only 1 register that we need to control. And this is how the exploitation path changes. Basically, we don't need anymore the first 3 registers, so the arguments are not, they don't need to be under our control anymore. We just need to control RAX, and then after we set RAX to 0xf, we will directly jump into a sig return syscall, and as soon as the syscall will end, it will automatically execute the execve syscall because we have also set RIP to the syscall instruction. So now in this example, only RAX control and the syscall gadget are needed. And specifically, I would like to note that RAX is a special register, so it's the one that it's usually used for storing return values of functions. For example, the read function always returns the number of bytes that it read from the file descriptor. So when I say RAX control, I don't necessarily mean that we need to have a gadget for that. It could also be that we can use the program itself in order to manipulate the value of RAX and make it value 0xf. Okay, so this is a very short snippet of how we can perform this kind of attack on Pawn tools. Pawn tools, for the ones that are not familiar with it, it's a Python module that is very useful, like, I don't know, always used for CDFs in general. But specifically for Pawn, for binary exploitation, it has a lot of very, very cool features. And here in the first 2 rows, we are just faking that we have the address of a binsh string. It's just for making you see how you can use it. And we are also faking that we have a syscall instruction at that address. They are just dummy addresses. Then what we do is that we call the sig return frame function from Pawn tools that we just need to specify which architecture we want to work on, and it will already return us a structure. And we can easily, very, very, very easily set all the registers just using the fields of the structure. And we can then set all of them exactly as we've seen before. So execve, this constant is just 0x3b, the one we've seen before. And then the address of binsh, 0, 0. And again, as we've seen, we also edit the value of RIP to the address of a syscall instruction. So here you can also find the link to the Pawn tools documentation, which is very well made. So if someone wants to go a bit deeper, you can find it here. And this was all for the first technique. So now we can jump to the second one. Okay, so we will start again with putting ourselves in a scenario. So here again, we start from the same statement as before. So we still have like a very big buffer overflow, for example, and we are able to override some return address inside the stack in order to hijack the control flow of the program. Then we also know that the binary is dynamically linked and it's partial rel-row. We will see what partial rel-row means in the next slide, so let's forget about it for now. Then we also know that we don't have any syscall gadget inside the binary, and this means that the attack we've just talked about, we cannot perform it because we don't have the syscall instructions we would need to execute both execv directly or sig return syscall. And then we also assume that we don't have a way to leak the remote libc or the remote libc addresses. Maybe it's a custom libc, so we cannot really perform all those kind of attacks. They are usually called ret2dlresolve attacks. If you're not familiar with ret2dlresolve attacks, it's not a problem at all because it's out of scope for this talk, so I will not talk about it. But just know that it's a class of attacks where you basically hijack the control flow of the program and ROP directly inside the libc. We cannot do it now, so let's forget about that as well. Our goal is always to ROP and spawn a shell, so the same goal as before. Okay, as we've said, we will start with some background knowledge and we will define what partial rel-row means. In general, it means that all the symbols from the external libraries, for example, libc, are resolved, their addresses are resolved only at runtime and specifically only when they are needed the first time. So what happens is that when a symbol is referenced for the first time, so for example, when a function is called for the first time, then the dynamic linker is the one that has the duty of handling the resolving process and computing the real runtime address of that function, and then it will write the address inside the binary. The resolution happens in a function, using a function which is called dlRuntimeResolve, which is exactly the function that is giving the name to this attack, which is ret2dlresolve. And in general, this whole process is called relocation. So let's suppose that we want to call an external symbol, specifically the read function from libc. What will happen when we call it the first time is that the code that will be executed will not actually be the code from the read function. We will be pushed inside a redirection code. We will call it like this, and we will also mention it later, so let's keep it in our mind. We will be here inside this redirection code that will redirect us into dlRuntimeResolve, which is the function that will actually perform the resolving of the address. And then only at the end of this step, we will have the real libc address, and we can finally call the read function. But from now on, we already computed the real libc address, and we also already have written it inside the binary. So all the following calls will directly have it, and they will be executed immediately. A very important thing to know as regarding this process is that all the information for all the dynamic symbols in general and all the information about relocation are stored inside the binary, and there is some dedicated specific data structures made for handling all these operations. And another important thing to remember is that the function dlRuntimeResolve, of course, it needs to know which one is the symbol that we want to resolve when it starts its execution. And in order to understand which one it is, it takes a sort of reference to that symbol from the stack. So we have to remember that in some way, this function takes from the stack a reference that tells the function itself, okay, this is the symbol that I want to resolve. Okay, now we can finally get to the exploitation part. So with everything we have seen and with everything we have in our minds now, we can ask ourselves, okay, how we can use this, how we can abuse the fact that all the information about dynamic symbols and relocation is stored inside the binary itself. In the same way as we did before with the other attack, what we do is create fake stuff inside the binary. So we always create a lot of fake stuff in order to fool the components of the binary. And what we do now is that we fake all the relocation structures that are needed for a specific symbol. And in this way, we can trick the dynamic linker and make it think that we are performing a legit relocation, what we're actually just resolving whatever symbol we want. So what we can do is we will ask the dynamic linker to resolve the system symbol, because this is a libc function that lets us execute commands. And so if we are able to call system and to call it with the binsh argument, then we will also be able to spawn a shell. Okay, so with this goal in our mind, we will see now all the exploitation process. And the first thing we have to do is to somehow create those fake structures and then put those structures inside the binary. And they must be put, of course, into an area that must be readable and writable, because otherwise we couldn't write the structures there. Then what we do is that we use our ROP abilities, because maybe we forgot in the meantime, but our attack starts from us being able to hijack the control flow. So what we do is that we use our ability to hijack the control flow in order to set the first argument for the system call, because what we are doing is we are pretending like system is called in a legit way. So we also have to prepare the correct parameters inside the correct registers so that when it will be called, the parameters will be the correct one. And specifically, it will be in RDI. So we will set, using our ROP chain, RDI equal to the address of a binsh string. Then we will also, remembering what we've said before about the reference on the stack, we will have to set inside the stack a reference to those fake structures, and those fake structures will be the ones specifically crafted for the system function. And then finally, we can jump to the redirection code, and this is the reason why I named it that way before. So we will jump specifically to that redirection code that will call the DL runtime resolve function for us. So in the end, since DL runtime resolve is called, and it's called with the reference to the system fake structures, then the system address will be resolved and system will be called. And as I said before, it will be called exactly with the correct parameters because we took care of that before. Again, we can see a very small snippet because, yeah, Pawn Tools basically does everything. Every single attack in the world, it can do it. And we are just importing the binary inside the script, so just in order so that Pawn Tools have all the information about the binary. And then what we do is calling this function, which is ret2dlresolve payload. And what the function needs to know is the binary we're working with, of course, and then which one is the symbol that we want to resolve, and also which are the arguments we want this symbol to be called with when it will be resolved. And it's super cool because basically Pawn Tools directly give us back the structure where we can find the payload here, which is exactly the fake structures we've been talking about. And also, the cool thing about that is that it will also automatically give us a usable address. So we said before that we have to put those structures in a readable and writable area, and Pawn Tools will automatically locate a usable address for this. And then, in the end, we can finally build our ROP chain. So we're using the ROP module of Pawn Tools, which is, again, super useful because it can automate almost every kind of ROP chain. And what we do is that we take from standard input, because 0 is the standard input file descriptor, and we put our fake structures into the address that Pawn Tools gave us. And then we call this function, which is ret2dlresolve, which will take care of all the other steps of our exploitation path. So if we look at here, we're basically just doing all these ones just with that single call to the Pawn Tools module. So yeah, again, oh yeah, I forgot about the animations. Again, you have a link to the Pawn Tools documentation if you want to read more about that. And before concluding, I would just like to say that in general, every CDF challenge is different from the other ones. Every scenario in binary exploitation is different from the other ones. So we have seen some specific scenarios where these techniques work and they can be very useful. And of course, it depends on the challenge. Sometimes there could be some different situations, and I've linked you some blog posts, some very interesting blog posts that you can read in order to understand some similar but a bit different scenarios. And yeah, also for SROP, there's some very cool, there's a lot of interesting stuff on the web. This was just an overview of the techniques, but yeah, there's so many cool ways of making these techniques to work. So that's all. Thank you.
So that was awesome. Thank you very much. We are a little bit late in the schedule, so maybe we can have one question. I don't know if any of you have any question especially. Not really. So I'm gonna just ask you one question, and because well, most of the pen tester never is going to be touching this kind of exploitation because it just looks very complicated and even like magic. So I would like to ask you, like, how would you recommend people to get started in this kind of cool techniques?
Okay, yeah. ROP technique is definitely the one I would recommend starting from because it's just stack. You don't have to mess with the heap, which is such a hell to handle with. So you can start with ROP, and there's a lot of resources online, like ROP Emporium is a cool website where you can find a lot of information. And these are two not super standard techniques. So you should probably start with some very plain ROP chains without any like hack, like in this case. But yeah, I would definitely recommend it because I love it. So I hope everyone else will love it as well.
Okay, thank you very much, Giulia.
Thank you. Thank you so